Okay, welcome back to another session. So today we're going to go ahead and continue, and we're going to wrap up the semester by looking at our last topic of discussion, which is stoichiometry. And so really this is now the culmination of all the things that we've been doing up to this point. So everything we've done so far is really in preparation for this particular topic, so to speak, because now what we want to do is kind of make it as real as possible. So far when we talk about chemical reaction equation, for example, we're describing, okay, the ideal situation as to what happens when chemical changes occur, in terms of looking at what happens to a set of reactants as they change to become a set of products at the end. We talked about making connections in terms of being able to connect up the quantities based on a count of something to the mass measurement of that something using the molar mass and so on and so forth. We also learned how to name certain chemical compounds based on the chemical formula. We can give it a name or vice versa. If we know the name of the chemical compound, we can then figure out the chemical formula. And we also talked about the different kinds of chemical reactions that are possible. And what we want to do now is kind of put it all together and look at what happens when we look at a real life situation. For example, if I were to go ahead and want to produce, okay, a particular product for commercial distribution or for sale, how do I go about actually doing that in practicality? Well, most of the time, when we get ready for a chemical reaction that would give us some product to basically end up with, it doesn't make sense for us to kind of keep track of the count that we have been using up to this point. Counting by molecules, for example, or by atoms, or by moles even. Because as it turns out, it's not a convenient way of basically bundling things and measuring them. A much more practical method, of course, is to measure the amount based on the mass of something. So in order for us to actually bring chemical reaction into the real world, so to actually create some sort of product, we need to be able to somehow keep track of the masses of reactants and products in order for it to make it real, so to speak. And so that's what we're going to be doing. So we want to go ahead and connect up chemical reactions, and we'll be able to keep track of all the individual quantities in form of mass measurements for all the substances that are involved in a chemical reaction. This process is called chemical stoichiometry. And the first thing we're going to talk about is the fact that in doing this, we have to absolutely start off with a very important tool, which is the balanced chemical reaction equation. So that might be a good starting point. So let's take a look at the information that we can get from a balanced chemical reaction equation. So what is it that we are getting from here? So from a balanced chemical reaction equation, what is it that we are obtaining? Well, let's take a look at an example. Let's say I'm going to go ahead and produce a particular substance, where I combine carbon monoxide gas and hydrogen gas. In this case, I'm going to end up with this particular material, and this is going to be in the form of a liquid. It turns out this is methanol. This is actually wood alcohol, and so this is a substance that we're going to be produced using these two reactants. Now obviously in this case I have the chemical reaction equation, but it is not balanced at this point. So it might be good to go ahead and balance it. I'm going to put those numbers in front so that I can basically conserve particles in the reaction. So if you take a look, I have 3 and 4. I have 4 hydrogen over here. There's only 2 here, so I might be able to put a 2 in front of here. And so when I do that, I can put a 1 here, 1 carbon, 1 oxygen, 1 carbon, 1 oxygen. So this is now my balanced chemical reaction equation. So the question then is, of course, what information does this contain? Well, as it turns out, these numbers in front basically tells me something about the relative amount of substances, of the reaction, the relative count, basically. So I could interpret this as individual molecules, for example. So this could be 1 molecule of carbon monoxide reacting with 2 molecules of hydrogen gas, reacting to form 1 molecule of my methanol alcohol molecule here. But that's not the only way I can look at it. I can actually look at any kind of count, because this is really the lowest ratio. So I can actually multiply this by the same number, and if I have an equality in terms of an equation, either mathematically or chemically, if I multiply everything by the same factor, it will still remain balanced. So in other words, I can look at it in a slightly different way. If I multiply everything by 12, for example, I could also interpret this as now 1 dozen of my carbon monoxide molecule to 2 dozens of my H2 molecule to 1 dozen of my methanol molecule. So that's perfectly okay as well. It will also be a balanced equation. I could also go even further. Instead of multiplying by 12, I can multiply by, let's say, 6.022 times 10 to the 23rd, which is then what? Avogadro's number. Then I would then have that many molecules of this, plus 2 times that many this, and then so on and so forth. But the idea is that we want to make things as simple as possible. So the one that we really want to interpret in terms of is we're thinking of these numbers as now number of moles, because that's a lot more practical in terms of reality. Okay? We can actually handle 1 mole of carbon monoxide much more readily than we can handle just a single molecule or dozen molecules of carbon monoxide. So really think of this as 1 mole of carbon monoxide gas combining with 2 moles, okay, of H2 molecules, forming 2 moles, okay, of CH3OH. If we have that, oh sorry, this should be 1 mole over here. Got to grew a little bit. 1 mole over there. So if we have this in mind, then we know that these numbers represent a count of the substances that are in this particular chemical reaction equation that's been balanced. Okay. So once we have them out, what does that do for us? How does that help us now in understanding how we can use this to go further in terms of looking at the relationship between the different substances? Well, we can now go ahead and take a look at the mole-to-mole relationships between the various substances, or what we call mole ratios in this particular scenario. So let's take a look at the following. Let's look at what we call mole-mole relationships and see how we can get that information off of a balanced chemical reaction. So let's think in terms now of a mole-mole relationship and see what we can get from this particular view. Let's use another example. This time, let's take a look at what happens when water decomposes. So let's say I have H2O liquid here, becoming H2 gas and O2 gas. Okay. Of course, if I were to go ahead and balance this, I find that I will have 2 here, and 1 over here. So that's the balanced chemical reaction equation. Okay. And so if we have this reaction equation, this is telling me that 2 moles of water molecule can then decompose into 2 moles of hydrogen gas and 1 mole of oxygen gas. So that's what we know from this equation. But what if I don't have 2 moles of water? What if I have a different amount? So what if, for example, I start off with 4 moles of H2O? Okay, so if I'm given 4 moles of H2O, the question may be, how many moles of H2 and O2 will I produce? How would I find something like that? Well, I could do the following. I could go ahead and say, well, what if I multiply this balance equation by some factor, the same factor all the way through, so that it stays and remains balanced? And I want to go ahead and basically make this number in front of my H2O look like this, look like 4, for example. Well, the way I would do it is I can go ahead, I take this whole thing and I multiply it by 2. So I have here 2H2O, liquid, giving me 2H2 gas plus O2 gas. If I multiply this whole thing by 2, then now this gives me 2 times to give me 4H2O liquid, breaking up into, now don't forget this distributes here, 2 times to give me 4H2 gas plus, and finally 2 times this 1 in front gives me 2O2 gas. So what this tells me is that, if I start off with 4 moles of H2O, then I can predict, based on this balance equation, that I will produce 4 moles of hydrogen gas and 2 moles of oxygen gas. And that seems pretty reasonable. This is still a balance equation, so everything that are connected are still going to be true. So the mole-to-mole relationship, basically, although the numbers are different, they still have the same relationship. Here, this is a 2-to-2 or 1-to-1 ratio. This is 4-to-4, also a 1-to-1 ratio. 2-to-1 ratio here, 4-to-2, also a 2-to-1 ratio, and so on and so forth. There's one thing I could do. Of course, this is not very practical because I could actually have a much different number over here that's not so easy to look at. So imagine, let's say, for example, instead of having 4 moles, what if I'm given a very odd number? So let's say if I'm given, I don't know, 5.8 moles of H2O, for example. So if I have 5.8 moles of H2O, then how do I go about figuring out how many moles of H2 and O2 I'm going to end up with? Well, I can still do the same thing, except now it involves a couple of different steps. So imagine now, if I try to do the same thing, I might now end up with something like this. I might have, let's say, starting off with 2 H2O. I'm going to go ahead and drop all the physical states, 2 H2 plus O2. Now, of course, it's going to be hard to multiply this thing by to give me this 5.8. We could do it, but sometimes it's kind of hard to see. So instead of doing that, what I could do is make sure that my coefficients up front is all 1 to begin with. Okay? So sometimes you may not be able to see that clearly. So if I go ahead and do this, what if I multiply this whole thing by 1/2? Okay, if I do that, then 1/2 times 2 gives me just 1 H2O. Then 1/2 times 2 gives me 1 H2 here plus, and then I have this 1/2 O2 out front. Now this is one of those weird situations where I now have a fraction for my coefficient. That's okay because this is still kind of temporary at this point. So let's see what happens next. Once I have that, then I can say, well, I want now 5.8 moles of H2O. So what do I do? Well, I multiply this by 5.8 all the way through. So I take this whole thing again, and this time multiply by 5.8 to everything in this case. When I do that, I end up with now 5.8 moles of H2O, giving me 5.8 moles of H2 plus, in this case, 2.9 moles of O2. So if you look at this, as it turns out, this is still going to be a balanced equation. So if you kind of divide everything by 2.9, you still get back 2 to 2 to 1. But now you can see that if I start off with now 5.8 moles of H2O, I can now say, well, if that's the case, I should end up with 5.8 moles of hydrogen gas and 2.9 moles of oxygen gas. Okay? So we could do it this way, mathematically, kind of just force our way from our initial balance equation to this new balance equation that give us now the appropriate numbers based on what this is. But that's going to be very inconvenient. It relies on a lot of manipulation of numbers and so on and so on. So is there an easier way to actually get to the same result? And the answer is yes. Okay? And that basically falls under the idea of comparing the ratios of the individual substances to each other. Okay? So this idea of now, instead of, okay, you can call this now the mole ratio method. So the mole ratio method really works like this. It's really kind of like a conversion type of problem, unit conversion kind of problem. All you're doing is you're looking at an equivalency between two things that will give you an equivalent statement that will then can be used to create a conversion factor. So in this case, I can pick any two substances that are in this reaction. Since I have 3 substances here, if I pair them up 2 at a time, I'll basically get 6 pairs. Okay? And each of those pairs will now give me a ratio of the coefficients up front. So for example, if I'm interested in the ratio of water to hydrogen in this reaction, what would that look like? Let's kind of get rid of this and create those ratios over here. And then we're going to apply those ratios to our calculation a bit later on. So in this case, if I look at the ratio of H2O to H2, this ratio, if I look at it in terms of number of moles of each that participates in this reaction, I find that there's a 2 in front of the H2O, and there's a 2 in front of the H2. So the ratio is really 2 to 2, or actually, in this case, I can simplify and say 1 to 1 ratio. Okay? So this is the ratio of water to hydrogen in this particular reaction. So I can pick any 2 substances. It doesn't matter whether they're reactants or products, it doesn't really matter. Any 2 substances. I can now do the same thing now, except this one, of course, I could actually flip it around if I wanted to. So if I flip it around and look at the ratio of H2 to H2O, well, guess what? That's still going to be my 1 to 1 ratio. Okay? It's 2 to 2, simplified to 1 to 1. So that's 2 so far. What's the next one? The next one, I can look at the water as compared to the oxygen over here. So I can now do a H2O to O2 ratio comparison. In that case, there's going to be a 2 in front of the water and a 1 in front of the oxygen, so this is now a 2 to 1 ratio. So in this reaction, there's always twice the amount of water as compared to the oxygen that is produced in the reaction. Okay? And then, of course, if I go ahead and flip that around, H2 to H2O, that'll now give me a 1 to 2 ratio. Okay? And finally, I can now look at comparing these 2 last substances here. So H2 to O2. So H2 to O2 is now 2 to 1. And then finally, O2 to H2 is now 1 to 2. Obviously, of course, as I add more substances into the reaction, the number of possible ratios that comes up is going to be much greater. But that's okay. I don't have to generate all of them. All I need to know is how I actually am able to do so. All I did was kind of pick any 2 and then put one over the other and then place the coefficients in the same order. Okay, so that's how I can generate all of this. So what do I do with all this now? Well, let's take a look. Remember our previous problem? I said that, well, what if I start off with, given 5.8 moles of H2O, and I want to find the number of moles of H2 and O2 that I would produce. Well, instead of doing that, multiplying everything by the same number kind of stuff, I can now do a mole ratio calculation, just like doing a unit conversion calculation. In that case, I always, just like before, start off with what I'm given. So if I'm given 5.8 moles of H2O, Then I say, well, what is the conversion now between moles of H2O and moles of, let's say, H2, one of my products. So I can go ahead and do this. Since this is not on here, I will now get rid of it by putting it into the denominator. So moles of H2O, moles of H2O here. And on the top, I now want to put mole of H2. That's what I'm looking for. So just like before, if you know how to do your unit conversion, this has no difference. This is the exact same kind of process. Now the moles of H2O goes away. The question is, what numbers do we use here? Well, this is where the mole ratios come into play now. So here I have H2 over H2O, so that's this ratio right here, H2 over H2O. So this is a 1 mole to 1 mole relationship. Okay? So I'm going to work this out, end up with 5.8 moles of H2. Okay? And if you recall, that's the exact same number that we had earlier over here. Okay? Now what about for O2? Well, again, do the same thing, 5.8 moles of H2O. And in this case, I'm now going to go ahead and convert from H2O to moles of O2. So now I look for a different ratio. Here, O2 over H2O. That's this one over here, O2 over H2O. Now I have a 1 to 2 ratio. That goes away, giving me just the moles of O2. And guess what? I end up with my 2.9 moles of O2 once again. So I get this exact same answer that I got from the previous method, but instead of just playing with math, I now have a very concise process where I look at the ratio of one substance to another in this chemical reaction and use that for a kind of like a conversion type of process to get to my answer. And so given the number of moles of any of these substances in here, you'll be able to identify the corresponding amount of that substance based on these coefficients, based on those coefficients of the balance equation. So that's the mole ratios process. All right, so in this case, why do we even bother doing this? Well, because once we're able to compare moles of one substance to the moles of another substance, then it's just one more step. It's going to add in now the next step where we connect up moles of substances to now the mass measurement. So instead of giving a substance in terms of its moles, I can now give you a substance in terms of its mass and be able to now use that to calculate its relationship to any of the other substances in the reaction. So let's see how that works. So let's go and bring now mass calculation into play. So how does mass now come into play? So the key is, again, making sure you understand where the connections are. In this case, we have made the mole-to-mole connection using the coefficients. The next step now, of course, is to make the mass connection. Okay? So in the next one, let's take a look at mass calculations. Oops, oh, this is dead over here. So let's take a look at mass calculations. So let's use another example, okay, see how this works. So let's assume that we're looking at now a combustion process of propane. So propane combustion. Okay. What does that look like? Well, propane combustion basically is going to be C3H8 is the chemical formula. So it is a hydrocarbon. Okay. So C3H8 is going to be in the form of a gas. We'll combine now with O2 gas. And what is it going to produce? What are the results? You should all know by this, right? By the time you look at the fact that you have carbon, hydrogen, oxygen, by the time you get to the other end, you should end up with CO2 plus H2O as your product. So CO2 gas, H2O gas here. Next step, of course, is to go ahead and balance the equation out. Okay, let's balance this out. So if I look over here, I have 8 hydrogen over here. I only have 2 hydrogen over here. So it looks like if I put a 1 in front of here, I can then put a 4 in front of here, giving me my 8 hydrogen. Then the 1 in front gives me 3 carbons. So over here, let's put the 3 here, 3 carbons. And then 3 times 2 give me 6 plus 4 give me 10 oxygen. So they put a 5 over here. Okay? So the very first thing you need to have in order for you to do this type of stoichiometric calculation is you must have a balanced chemical reaction equation. So that's the first thing you need to make sure you have, okay? A balanced chemical reaction equation. Once you have that, then the next step is, okay, what are we looking at? Well, in this case now, my question might be, well, what is, okay, the mass, okay, of my oxygen gas needed, okay, to react with, let's say, a given amount of my propane. So let's say with 96.1 grams of my, okay, propane gas. So how much oxygen do I need now in order for me to kind of use up all of this propane to produce carbon dioxide and water, okay, to burn it all up, so to speak. So notice in this case now, okay, I cannot compare grams of substances right away, because these numbers up here only allows me to compare counts, the moles of substances. So just like before, just like when we did the empirical formula calculation, for example, in order for us to kind of determine the subscripts on chemical formulas that describes either molecules or moles, we need to first convert mass to moles, and then from there we can compare the number of moles and so on and so forth. This is the exact same thing. Okay, I need to go ahead and convert grams of my substance into moles of substance. Moles of substance. So let's kind of take a look at in terms of the strategy. What is it that I'm going to be doing? Well, first of all, I'm going to take the mass of substance 1, whatever substance I'm starting off with that I'm given. From there, I need to go ahead and convert this to now moles of substance 1. So this is the first conversion from mass, change it to moles. And of course, it doesn't have to necessarily be moles. It could be some count of some sort, in general. And then from here, once I have the moles of that substance, then I can now compare it to the moles of other substances that are in the reaction itself. So now I'm looking at comparing it to the moles of substance number 2, whatever I'm interested in. So in this case, what is my interest in? Well, my interest is going to be for oxygen. So somehow if I convert the mass of my propane into moles of propane, then I can relate that number of moles of propane to a number of moles of my oxygen. That's my second substance. Then once I have the number of moles, since I'm looking for mass, I would then convert that back to mass of substance number 2. So that's going to be the strategy involved in terms of how to proceed from one point to another. You're always starting off with what you're given, and then you have some target. So what's given is your number 1. What you're targeting is going to be your number 2 right over here. And sometimes, of course, the mass could be different units, so it may not necessarily be a gram unit. So in that case, you might need to do some conversion to begin with. You end up with grams, as we'll see a little bit later on. But the idea is that you can have some sort of measured value converting to some sort of counting value, and then you relate the counting value of one substance to the counting value of another substance, and then relate it back to some sort of measured value in terms of mass and so on. So let's see how that works. So in this case, let's go ahead and start the process. So the first thing I need to do is start off with what you're given. So I start off with 96.1 grams of C3H8. So the first step is going from mass to mole. You know how to do this now using what? The molar mass. So here I will then get rid of grams of C3H8 over here. I will put down moles of C3H8. So here's my first step, going from mass to mole. Well, for 1 mole of C3H8, if you go ahead and add up 3 carbons with 8 hydrogen and so on and so forth, you end up with a value of, I believe, 44.09 grams. So that's your first calculation. Now then give you moles of this substance, moles of that substance. I could put down an intermediate result, but as it turns out, I don't need to. As it turns out, just like in unit conversion, you can continue to convert until you get to the unit that you're interested in. So let's go and continue. I don't want moles of C3H8. I want somehow end up with mass of O2. So what's the next step? Well, now I connect up moles of substance 1 to now moles of substance 2. So moles of substance 1 was this guy over here. This is now substance 2 right here. So this is number 2. This is number 1. So where are they connected? Well, they're connected right up here. Right up here. So here is number 1 over here. And here is number 2 right over here. So this is then the connection right here. So now you go ahead and put that into here. The next step, I can then connect up from moles of C3H8 to moles of my interested substance, O2, right over here. And the ratio now, in this case, for every 5 moles of O2, you basically use up 1 mole of C3H8. So this is now 5 to 1 here. Now the moles of C3H8 no longer exists. Okay, that's gone. So now I have moles of O2, not quite what I want yet. Remember, I want what? I want mass of O2. So now I take this next step right here. So this was the first conversion, taking you here. This is the second conversion. Now I have a third conversion right over here. So the third conversion will now look like this. This is again something that we know how to do, going from moles of O2 now to grams of O2 using the molar mass. So each mole of oxygen is what? 15.9994 multiplied by 2. That comes up to roughly 32.00 grams of O2. So now moles of O2 goes away. All this now give you one last product, which is now going to be units of grams per O2. That's exactly what I'm looking for, mass of O2. And then now you can go ahead and put the numbers in. And if you put all the numbers in, you end up with about 350 49 grams of O2. So what this does, it effectively allows you, okay, to use a balanced chemical reaction equation to keep track of the, okay, different substances that are involved in this reaction. So if you know something about one of them, you can then find out something about the other. So I know the quantity of one, I can now find the quantity of the other. So given that I want to use up this many grams of propane, I can now determine the number of grams of oxygen that I would need in order for that to happen, in order for them to react. Of course, this is in the ideal situation. So when I combine 96.1 grams of C3H8, I expect to use up 349 grams of O2. So all of them then gets converted into carbon dioxide and water, okay, as my product at this point. We'll see what happens if, okay, one of the substances get left over later on, okay, later on in the chapter. But for now, okay, this allows you to kind of calculate and relate quantities between any two substances that you have in a balanced chemical reaction equation. And again, this can be generic. It could be for any kind of scenario that uses the same kind of idea. Okay? The idea of some sort of, okay, measured quantities or some sort of counting quantity and so on and so forth, and be able to kind of jump back and forth. The equation actually keeps track of count ratio, a mole ratio, for example. Okay? So you cannot compare grams using these numbers. So you must keep that in mind. All right, so once we have that, so let's go ahead and take a look at a more generic way of looking at this. So we can kind of see the underlying principle and not worry too much about all the nitty-gritties in terms of the numbers themselves. So let's take a look at, instead of looking at chemical reaction, what if we have to make pizza? So let's apply the same principle now to the idea of making pizza and see how that actually works out the exact same way. So let's assume that I want to go ahead and make some pizza. Okay. So I have, of course, a certain formula, so to speak, that I will use to basically make my pizza. And let's say, of course, I have to start off with pizza dough. So I basically get some dough. I can now go ahead and work that, and using the dough, divide it up into individual pizza balls that I can then stretch out and form the crust of my pizza. And I'm told that if I have 1 pound, okay, of dough, I can go ahead and create 4, okay, dough balls. Okay, so each dough ball will basically allow me to make 1 pizza, basically. Okay, so 4 dough balls. So 1 dough ball basically gives me 1 pizza. So that gives me the crust of my pizza. Of course, nobody just wants to eat the crust, so we need something else to put on there. Of course, instead of looking at everything, I'm just going to look at one thing I'm going to put on there. I'm going to put on their pepperoni, okay, little pepperoni slices. So let's assume that for every 1 pizza, I'm going to go ahead and put 24 slices of pepperoni. Okay, 24 slices of pepperoni. And where is this pepperoni going to come from? Well, it's going to come from a big package that is sold by the pound, for example. And so I am told that 1 pound, okay, of pepperoni, okay, is going to have, I think, in this case, 72 slices of pepperonis. So I have all this information over here. These are kind of like now my, okay, conversion factors. So these are kind of like the mole ratios, so to speak, in my chemical reaction equation. I don't have quite the equation over here yet. So what does it look like? Okay, well, it might look something like this. In general, I will say that, okay, if I have 1 dough ball, if I add to it 24 slices of pepperoni, okay, that will then equal, in this case, I just go ahead and use the arrow, that will then produce 1 pizza. So this is really now my chemical reaction equation, so to speak. And these are now my coefficients that relates the count of substances that are in this particular reaction. So I have 1 dough ball plus 24 slices of pepperoni will give me 1 pizza. So with that in mind now, I can now ask the question, well, what if I'm given a certain amount of the dough? So let's say I am given, okay, 3 pounds of dough. Okay, so that's what you're given. So the question is, how many pizza, okay, can I make? And then, oops, so produced. And also, how many pounds of pepperoni do I need? Okay, so how would I find this information? So that way I can gather all my ingredients so that I can actually make my pizza. So what do? How many pizza can I expect to get at the end of my journey? And how many pounds of pepperoni should I go ahead and buy, knowing that I have 3 pounds of dough. So what I do? Well, I use the idea of the mole ratio based on these numbers over here, and then do a unit conversion type of process. Okay, so this is the core of, again, your stoichiometric process. So you start off with what you're given. So you're going to start off with 3 pounds of dough. Okay, so this is now the measured quantity. Measurement could be the same as, grams of something, for example, kilograms of something. Then we need to kind of convert it to a count. So where's my count? Well, I can now say, well, pounds of dough would then be equal to some sort of count in terms of what? Well, dough ball, right? So the dough can be now used to make the dough balls over here. So this would then give you a certain number of dough balls. And according to this connection right here, for every 1 pound of dough, you have 4 dough balls that you can make. Okay? So now pounds of dough cancels out. We now have a certain number of dough balls. But we also know that, okay, if I have a certain number of dough balls, I can now create a certain number of pizzas according to this particular reaction here. So I know that for 1 dough ball, I can produce 1 pizza. So right away, I can say, okay, if I do that, I can now make the next conversion. Dough balls connecting to pizza, 1 pizza per dough ball. So now that goes away, giving me 3 times 4 times 1, 12 pizza expected at the end of the process. Okay? So that tells you how many pizza you should end up with at the end. In the same way, you can also now calculate the number of pounds of pepperoni needed. So notice in this case, okay, I am relating different substances in each of the terms. The first one I related dough to pizza. Now I related dough to pepperoni. Okay? And the intermediate, of course, is that dough ball here, and then we'll see what happens in this case. So if I start off again, 3 pounds of dough, okay. Now in this case, to kind of look at this, I can first make sure I have the number of dough balls first. So again, I need the number of dough balls. So this first conversion still looks the same, 4 to 1. Okay, so now I have the number of dough balls. Once I have this, I can now see a relationship between the number of dough balls and number of slices of pepperoni that we need. I need 24 slices for each of the dough balls. Now, that's my next conversion. Okay? So now I go to dough ball, and basically slices. Well, I'm just going to say slices of pep. Okay? In this case, it's going to be 24 slices for every 1 dough ball. So that goes away. So now I have a number of slices, but that's not what I'm asked for. I'm asked to find the number of what? Pounds. That's where now this last connection comes in, where there's now 1 pound for every 72 slices of your pepperoni. Now the last conversion is, oops, slices of pepperoni to pounds of pepperoni. And we find that for 1 pound, you would have 72 slices. So that now goes away. Okay? So when you look, you started off with pounds of dough, and now you ended up with pounds of pepperoni. And that's exactly what you're looking for. But you notice each step is a conversion process, right? You go from a measured amount of something to a count, and from that count, you go to another count. So count of substance 1, dough ball, to a count of sliced pepperoni, okay, substance 2. And then from there, from the count, you go back to a measurement, okay, in this case, pounds. So you work all that out, you end up with 4 pounds of pepperoni needed to make the 12 pizzas, okay, 12 pizzas. And so although this is talking about making pizza, it works the same way as if you were doing chemical reactions. And it's just that the units might be a little bit different, the substance is a little bit different, but the process is exactly the same. And so that's why I have now a particular reference sheet you can now pick up from La Lima. And this basically reference sheet basically gives you a general breakdown on how to proceed with this type of stoichiometric calculation. There is a step-by-step written instruction as well as sort of a flow chart instruction. So you can use either one, whichever one you're more happy with, and use that to kind of help you with the initial decision-making process as you progress from one substance to another in comparing them in a chemical reaction stoichiometric calculation like this. Okay. All right, so let's do one more example. Okay, what can we use this for? Well, we can actually use this for comparison, for example, in terms of comparing 2 different reactions and seeing the outcome and so on and so forth. So let's take a look at another example to see how this process can be used. This time, we're going to go ahead and compare the effectiveness of different antacids. So if you have too much stomach acid, for example, well, stomach acid is pretty much just hydrochloric acid, a form of hydrochloric acid. If you have too much and you get an upset stomach and stuff like that, well, you want to take some antacid, it's going to settle, because the antacid will do what? Will actually neutralize the acid in your stomach. So basically, it's some sort of basic material. Okay, so that's the idea. So let's take a look at doing stoichiometric calculations in general, and comparing the two types of stoichiometric calculations, and making a comparison. Okay? In this case, we're going to go ahead and compare two reactions. Okay, comparing two reactions. And so let's see what these reactions are. The idea is that we want to go ahead and react hydrochloric acid. So this is your stomach acid, HCl, okay, plus, and now we'll go ahead and put two different things in here and see how each one react with it. The first one is pretty straightforward. Okay, this is of course just baking soda, sodium bicarbonate. Okay, so this is your baking soda. So this is something you can actually not find in your cupboard in your kitchen and so forth. The other one is going to be a little bit more of a commercial product. This is going to be what I'm going to use. Okay, okay, let's use magnesium hydroxide. Okay, so MgOH. Okay, 2. Okay, magnesium hydroxide. And in this case, this is going to be in a solid form. That's going to be a solid form. Okay, sometimes people refer to this as milk of magnesia. So basically, you have solid magnesium hydroxide suspended in a liquid base, basically. Okay, so it's not a solution, but it's really a suspension. But that's your milk of magnesia that you can get, commercially at Long's or wherever. So let's see which of these now is more effective in neutralizing the acid. And so in this case, okay, we're going to go ahead and look at the following question. Okay, which acid, okay, can better neutralize, okay, HCl, okay, there. In this case, of course, I'm going to compare them by looking at the same amount. So let's assume that I have 1.00 grams of NaHCO3 versus 1.00 grams of my MgOH2. Okay, see which one is going to give me better results. Okay, so I start off with the same mass, and I want to ask now, if I completely use up this particular material, then the question is, okay, really what I'm asking is, how many moles of HCl, okay, do I neutralize? Okay. So that's what I'm looking for, in the number of moles of hydrochloric acid that I can neutralize based on this amount of each to start off with. So let's start off with my sodium bicarbonate first to see what that looks like. In this case, obviously, I need to go ahead and write down a balanced chemical reaction equation. That's always where we start off. So let's take a look at what that looks like. So then we're going to have NaHCO3, a solid, plus HCl aqueous. So what is that going to give me on the other end? Okay, what you find is that this is going to end up with, in this case, as it turns out, sodium and chlorine. So you have sodium chloride aqueous, okay, plus, and the other thing is going to be, of course, water and carbon dioxide. H2O, okay, liquid, plus CO2 gas. There's a little bit of gas at the end, right? So now, of course, I need to go ahead and balance all that out. And if you work out the balancing, well, that's kind of nice. That's pretty easy, actually. It's 1, 1, 1, 1, 1. Okay? So if you kind of check, you have, okay, in this case, 2 hydrogen over here, 1 here, 2 hydrogen, 1 sodium, okay, 1 chlorine, and then 1 carbon, 2, 3 oxygen, 3 oxygen. So everything looks good. Okay, so it just happens to be a really nice equation in that case. And so in this case, what I'm interested in, of course, is I'm interested in my sodium bicarbonate, this guy right over here. So this is my substance number 1, and I'm interested in its action on this guy over here, which is now my substance number 2. So you have a certain amount of this substance number 1. The question is, how much of substance number 2 do I need now to completely react with this to give me the products on the other side? That's what I'm looking for. Okay? So knowing that, I can now go ahead and start off by knowing this amount of substance number 1. So I'm given 1.00 grams of NaHCO3. That's my substance number 1. I want to go ahead, the first step, of course, is from the mass, I want to change it to moles. So I have grams now, NaHCO3 to moles of NaHCO3. So So for 1 mole, again, you just need to add up all of your contributions in your chemical formula, and you find that the molar mass is roughly 84.01 grams, okay, per mole of sodium, okay, bicarbonate. Okay. So now you have this first part, grams go away, you now have number of moles of your substance number 1. Once I have the moles, I can now compare them mole to mole, so to speak, using the mole ratio. So the next step, of course, is now go ahead and use the mole ratio from the equation. So now I have moles of NaH, CO3, and then this is now moles of HCl that I'm going to be combining with. So in this case, if you look, well, that's kind of nice. It's a 1-to-1 ratio. So then that goes away. Now I have number of moles of HCl, which is exactly what I'm looking for. So now I've arrived at what I'm looking for. If I were to ask, what is the number of, what's the mass, then you can take one more step and find the mass at that point. And if you go ahead and calculate that, you end up with, okay, 1.19 times 10 to the minus 2 moles of HCl, okay? Notice in this case, I have 3 sig figs to start off with, so my answer will also have 3 sig figs, okay? So that's the first part right over there. All right, so 1 gram of sodium bicarbonate will basically neutralize, okay, 1.19 times 10 to the minus 2 moles of HCl. The next step, of course, is going to now do the same thing, except now for the magnesium hydroxide. So let's see what that would look like. Now I start off with, okay, magnesium hydroxide. Now I have Mg, okay, OH2 solid plus HCl aqueous, okay. And so in this case, when you look at this, you're going to end up with magnesium chloride. It's going to be aqueous, okay. And at the same time, you're going to go ahead and have, okay, H2O, okay. Let's go ahead and get that part over there, okay. And so interestingly enough, in this situation, okay, you basically produce water and magnesium chloride. No gas, which is actually kind of good. Okay? You already kind of guessed, you don't want gas. Okay? So this one doesn't have any gas. Let's see what happens. Now again, you need to kind of balance this out, and if you work out the balance, you find that you have 1 here, 2 here, and then you have 1 here and 2 here. So if you check this to make sure, 1 magnesium, okay, 2 chlorides, okay, and then 1, 2, 3, 4 hydrogen, 1, 2, 3, 4 hydrogen, then 2 oxygen, 2 oxygen. Everything balanced out. So that looks pretty good. So once you have that, now you can go ahead and do your stoichiometry calculation. You're given, in this case, 1.00 grams of your magnesium hydroxide. So the first step, of course, is going from measured quantity to count quantity, so mass to mole. So grams of MgOH2 to moles of MgOH2. So for 1 mole, if you add up all of the molar for this, you end up with 58.33 grams of magnesium hydroxide. Okay, so that's your first step. Once I have now the moles of substance 1, I can now go to comparing it to moles of substance 2. This is substance 2 right over here. Okay, that means the next step, of course, is moles of MgOH2 now to moles of HCl. Notice that I always write down the substance so I know which one it is, so I can kind of cancel them properly. So otherwise, if you just have moles all over the place, that might be kind of confusing. Make sure you identify your substance. So this now obviously goes away with this. Now these numbers would then be for 2 moles of HCl, 1 mole of MgOH2. Okay? So now I end up, oh, there's my moles of HCl, which I'm looking for. So this will give me moles of HCl. If I work that out, multiply everything out, you end up with 3.42 times 10 to the minus 2 moles of HCl neutralized. So by looking at these two comparisons, you can see obviously in this case, okay, that the 1 gram of magnesium hydroxide does a much better job of neutralizing hydrochloric acid than 1 gram of, okay, your baking soda. So that's why you don't go ahead and grab baking soda from your kitchen and swallow that for heartburns and acid indigestion and so on and so forth. Okay? In this case, milk with magnesia is a better product, okay, for 1 gram. So that's going to be the idea behind this process, okay, comparing substances, okay, based on that balanced chemical reaction equation. When we come back next time, we're going to continue talking about, for example, okay, the percent yield for your calculation, also limiting reactants and so on and so forth. And then we have probably a couple more sessions before I wrap everything up in this situation. Okay? All right, so between now and Thursday, make sure you go ahead and continue reading and get started working on your homework assignment. And I'll see you guys on the next Zoom meeting. And so in the meantime, take care. I'll see you next time.